So jump in your book. It's somewhere probably 85 maybe. Okay, so what I want to talk about is how we really are going to try to beat the system with AP. Now, you remember the very first day we started derivatives, we talked about this ugly limit definition was actually a derivative. And we did a couple problems with it. It was just awful. I mean, very tedious, very long. And because of that, I try to avoid it. And there was a page in early on that very first day that I said, just ignore that back side of the worksheet. I said, just ignore that. But here's how sometimes you can beat the system. I'm going to show you two ways to do it. But the first thing I want to do is help you to see that this is not the only definition of a derivative. This is also a definition of a derivative. And this one shows up in APCalc probably as frequently as this one. Now, when you look at all of these problems, you may not see the definition of derivative at all. What you might see is just a limit. And that's okay, because I'm going to show you today how to do all of these with L'Hopital's rule. Okay, so I've mentioned L'Hopital's rule a number of times, so we're going to talk about actually how to do them with L'Hopital's, but I also want to show you how you could do them if you recognize that it's actually a derivative. Okay, so in this definition, this one's kind of easy to recognize because you see these H's in there. So when you, and I don't believe any of these have the H because I'm talking about this alternate definition today. But if you ever see a function and you see this x plus h or 2 plus h or just a bunch of h's, that should be a red flag that that's a derivative. Well, this is another red flag for you. And again, you might look at this right now and go, all I see is a limit. And that's fine. And I'll show you how to do those with L'Hopital's rule in a second. But if you look at this, if you ever see a situation, and all this is saying right here is, you would see a function with an x here and here on the front of the fraction, and on the back of the fraction, y'all with me? On the back of the fraction, whatever this value is shows up there, and then up here it would be whatever the y value is had you plugged that in. So let me just walk you through that. So right here, what I see is a function, ln of x, and just a single x. Well, that meets that part of the criteria. And then over here, if I plug an e squared into that function, what's ln of e squared? 2, and then there's the e squared. So you see the value of the function and the value you're plugging it in, and then the function and the variable x. So because I see that, I look at this and I go, oh, it's a definition of a derivative. And the function in question was ln of x. So what I could do, rather than treat it like a limit, I could say, well, if this function was ln of x, and this means the derivative of the function at x equals e squared, I could take the derivative of this, and what's the derivative of this? How do you take a derivative of a natural log? Put the x on the bottom, derivative it on the top, and then all I would have to do to find this is plug in e squared. And I get 1 over e squared. Look at this one. Does this meet those conditions? Now again, actually exactly. But if you miss it, it's going to be okay. Most people, I got to be honest with you, most people end up doing this using L'Hopital's rule. But I just wanted to give you an alternate way to do it. If I look at this and all I see is a limit and I plug in the pi over 2, I get 1 minus 1 over pi over 2 minus pi over 2, I get 0 over 0. And I can use L'Hopital's rule and I get 0 over 0, which we'll do on the back side of the sheet. But if you look at it and go, wait a minute, there's the function, there's the x, there's the value I'm plugging in for the x, like the a, and then this would be what sine is when I plug a pi over 2. Well, that's function, what the function is at a, x a. There's the function, there's what the function is at pi over 2, x pi over 2. So when I see that, oh, this is the definition of a derivative. The function was sine x, right? But since this means derivative, what I could do, everybody with me? I could take the derivative, which gives me cosine, and then what? Plug in the pi over 2. And I get cosine of pi over 2, which we know is 0. So this is what if you recognize that it's a definition of a derivative. If you do, then this is an alternative. And you'll see that when I show you L'Hopital's rule is essentially doing this. But you don't have to recognize you're doing it. And if you're in my class, you probably remember L'Hopital's rule, but let me just do a couple others. Okay? I'm just gonna jump around. So like, look at number 4. Number 4, oh man, all I see is a derivative. Okay, I mean, all I see is a limit. That's fine. If you plug a 4 in, you get 16 minus 12 is 4. 4 cubed is 64. 64 minus 64 is 0. Plug a 4 in here and you get 0. Now you could actually factor this. Isn't this a difference of 2 cubes? Block cubed minus 4 cubed? That would be an ugly factoring process, but L'Hopital's rule is going to work better for you. But if you look at this and go, wait, if this is my function and that's my x, there's my a value, and that is what I get when I plug 4 in here, all the boxes were checked, right? So if the function is what? What's the function? X squared minus 3x cubed. So if that's the function, what would the derivative be? And if you're asking yourself, why are you taking the derivative? Because that's what this means. This means the derivative of that function. But I don't have to do it this way, right? There's lots of ways to do a derivative. This is the ugly way. What I'm about to do here with the chain rule is the easy way. So all I got to do is go 3 law squared times 2x minus 3. And then all I have to do now is plug in what? The 4. So if I plug the 4 in, I get 3 times 16 minus 12 is 4. 4 squared is 16 times 8 minus 3 is 5. And what does that give me? 48 times 5, 240 maybe? And I've got my derivative. Is that right? Yeah. But, again, if you're looking at it still going, yeah, I don't know what you're talking about. You're going to be okay, because I'm not making you, you're going to see a limit like this on your derivative test. Hopefully you don't look at it and go, man, that jerk, I'm done with limits. First of all, no, you're not. But even though it's a derivative test, hopefully you'll look at it and go, oh, derivative test, I bet I can use derivatives. And sure enough, I did, right? Because I recognized that was a definition of a derivative. But I will give you another option, and the other option, L'Hopital's rule, works great on all of these on this page, with the exception of the x plus h ones. It works for those, but I find that people find it a little more tricky when it's an x plus h, and you'll see why when I show you in a second. So let me pick, I don't know, pick another one. 7, an x plus h one. Okay, now, here's how the x plus h ones would work. The definition of an f of a limit with this definition was this, right? Are you with me? So, what's the actual function? Okay, and this one, it's really easy to see, oh, it's cosine squared x, because it came straight from that, right? Honestly, on this one, it's not so bad, because if I think about, oh, you just plugged an x plus h into the function, you can still see that it's cosine squared of x. They just plugged an x plus h in. So the original function, I'll do it right here. If the original function is cosine squared x, and this is the definition of a derivative, then they were wanting me to find the derivative of cosine squared of x. So what's the derivative of cosine squared of x? From yesterday.
2 cosine.
Start with the 2, good. 2 cosine 1x, that takes care of the 2. Times negative sine x, good, I love what I'm hearing. That takes care of the cosine, times 1 if you will, but you don't have to put it times 1. Now here's the difference. On this one, I was taking the derivative with respect to the x. I wasn't given an x value, was I? On this one, on the other definition, x was approaching a value. So on the alternate definition, there was always a value to plug in. On this one, there is no value to plug in unless they give you the value right there and there. And if they give you the value right there and there, then that would be different. You would go back in the end and go, oh, x was replaced with a pi, plug a pi in. But if you look in the original, that's why I think L'Hopital's on this one is sometimes trickier, not trickier, but It's because they have two variables here, and that tends to confuse people a little. So had this been, instead of x plus h, had this been something like pi over 3 plus h, pi over 3, then hopefully you go, well, the function was cosine squared of x. That's the function. But what they wanted me to do was take the derivative when the x was what? Pi over 3. So if you had something in there for x, ignore it in this process and then go back and plug the pi over 3 in. Now, of course, you didn't have to do that on this, but you would have had to do that had there been a pi over 3 there. So I'm going to do this problem number 10 because 10 has 4 plugged in for what? X. Now, again, you might look at this and go, I do not see the definition of a derivative there. And you might not, and that's the beauty of L'Hopital's rule. Okay, but I'm going to show you why there actually is a definition of a derivative there. So when I look at this, I see 4 plus h. Whenever I see an h, that's a red flag to me. That, oh, maybe that's an x plus h. So I pretend for a second, all right, if that was an x plus h, right, then what would my function have been? My function would have been 1 over x, because I plugged in x plus h in for x. So if my function is 1 over x, what would be the derivative of that? Careful. What's the derivative of 1 over x? You got two options. One, quotient rule. What's low times the derivative of the high? The derivative of high is 0, right? So that's gone. Minus high times the derivative of the low. What's high times the derivative of the low? 1 times 1 over the low squared. That's one option. Or you could change that x to x to the negative 1 and do negative 1 x to the negative 2. But aren't they the same thing? Yep. Your call, either way. So, but where did they want me to take the derivative? When x was 4. So in this case, you would come in here and plug a 4 in, negative 1 over 16. Now, I just want to show you that because that is AP's intent for you. But man, intent schment, for like the last 20-something years minus the last 2, they haven't even made us learn like L'Hopital's rule. But I've been teaching L'Hopital's rule left and right because it's a great way to bail yourself out of questions like this, so you don't have to know this method. And in the last 2 years, they've said, okay, put L'Hopital's back on there. But I've said, you know what, it's been on there for me because I don't want to have to struggle through these kinds of questions. Not to mention, if you look at this, do y'all see a definition of a derivative? Somewhere in there, exactly. But because you see the x plus h's, right? Guess what the temptation is for the function? Let's just see. What do you think the function is? Okay, good. It is x to the 5th plus x squared. You know what I see a lot of people do? Grab that and say x to the 5th minus x squared. But if you're really thinking, wait a minute, if I really am going to set this up, I've got to factor that negative out. Oh yeah, blah to the 5th plus blah squared, blah to the 5th plus blah squared. That must have been this. And then the derivative must have been this. And since I didn't know what the x was, I leave it. And that's what you would end up with if we simplified this junk. But I'm not going to simplify that to the 5th power. I'm going to pull out Pascal's 5 row, 1, 5, 10, 5, 1, and have, no, 1, 5, 10, 10, 5, 1, and have a huge long polynomial, and then this, and then, no way. Not going to do it. All right, but that's what you would have ended up with. So, that gives you a taste of what I'm kind of trying to show you. But let me show you L'Hopital's rule, and I believe I'm using a lot of these same questions, if not all of them. So let's just walk back through these. And here's L'Hopital's rule. And you guys have it easy in L'Hopital's rule. Because in AB, they only make you know a couple of what we call indeterminate forms. And indeterminate forms are situations where you get like 0 over 0. Now, we've talked a lot about 0 over 0, right? We know there's a hole. And if there's a hole, there's a limit. But other indeterminate forms are like infinity over infinity, or infinity to the infinity, or 0 to the 0. We don't have to know those. We'll use those for BC calculus. We have to know these two. So bottom line, here's the thing. If you look at these problems and all you see are limits, it's not a problem anymore. Because if you start the limit and you go to do it and you get this, or this, in this class, then all L'Hopital's allows you to take the derivative of the top and the derivative of the bottom. Notice that's not the chain rule, right? I didn't do Lodi half minus side over low squared. Just the derivative of the top, the derivative of the bottom, redo your limit again. And if you still got 0 over 0, derivative of the top, derivative of the bottom, redo the limit again. And you just keep doing that until you get an answer. Now, in a rare case or two, you do that and you go, okay, I'm in this vicious cycle of never getting an answer and I'm never getting anywhere. Probably you made an error on the AP test if that happens, because I've not seen that. But in real life, sometimes that happens and you're going to have to find another way. But keep in mind, this is Cal 1, right? This is not Cal 10. I mean, there's plenty of calculus you will never learn, even if you get a math degree. I mean, you could get into calculus in a master's and a doctorate and deeper, study it the rest of your life if you wanted to. So let me show you L'Hopital's here. So hypothetically, you're taking this derivative test. Number 1 pops up and you're like, man, that's odd. Mr. Hurry put a limit question on there. Oh, well, I guess I'm just going to do the limit. So I plug a pi over 2 in and I get sine of pi over 2 minus 1 over pi over 2 minus pi over 2. And that gives me, what's sine of pi over 2? 1. I get 1 minus 1 over that minus that. But what does that do? That throws up a red flag that I am allowed to use L'Hopital's rule. And what does L'Hopital's rule tell me to do? Derivative of the top over the derivative of the bottom. So let's slowly walk through this. What is the derivative of sine of x? Cosine x times the derivative of x, which is 1. What is the derivative of 1? Negative 1? 0. What's the derivative of x? 1. What's the derivative of that? 0, because pi is a constant, right? Right? It's not a variable. So minus 0. So all I end up with is this. So, and by the way, recopy the word limit. Don't just do this work. AP gives you credit based on what you show them. And a lot of times it'll be a 2-point problem, and they want to see that you've done L'Hopital's. So they give you 1 point for showing you knew L'Hopital's, and then 1 point for your answer. And if all you do is go, oh yeah, plug it back in, you get 0, and you write 0 as an answer, you didn't show that step. So by showing this, heck, I'd probably even say by, oh, yeah, L'Hopital's looks like La Hospital without the S. By,
hospital though.
you what?
It's in French. It's hospital.
That's what I would say God's name, but it translates just to hospital.
Yeah.
Oh, it does?
Yeah, because I was.
How about that? I've never been told that.
L'Hopital, and it corrected to the French.
Yeah.
With the accents.
Huh.
The hospital.
Did not know that. Another thing about L'Hopital, L'Hopital worked with Euler. Take any physics, you know Euler's he's a pretty smart guy, done a lot of things. Well, evidently, Euler was like his mentor. And L'Hopital was trying to get on the map. This is actually a true story. Helmer's told me this, he discovered this somewhere. And he said, L'Hopital was trying to prove his worth as a mathematician. And he's like, Euler, man, can I just claim credit for this? I know we worked on it together. Really, it's probably more you than me, but, and he goes yeah, sure, whatever. And literally, L'Hopital's rule got all this math fame and calculus, but really it was more of another Euler rule. But anyway, by L'Hopital's, I redo my limit, and what happens now when I plug the pi over 2 in? I get a 0. Guys, all those problems we done in your limits test where you got 0 over 0, you could have done L'Hopital's rule if you knew it. I don't know if any of you did. I know half of you I taught last year and know L'Hopital's rule, but I don't think anybody applied it. Okay, which is okay, because I didn't need you. What about this one? You look at this on your test and you go, oh man, why did you keep giving me these limit problems? It doesn't matter. We just did this problem a second ago using that limit definition and undoing it. But watch, plug an e squared in there. ln of e squared minus 2, e squared minus e squared, ln of e squared is 2, up 0 over 0. What happens? Red flag, right? So what do? Derivative of ln x. What's the derivative of an ln x? 1 over x. What's the derivative of 2? 0. What's the derivative of x? What's the derivative of e squared? Not 2e, because e is a what? It's a constant. So what's the derivative of constant squared? 0. Redo your limit. And when I redo it, what do I get? 1 over e squared. Now, if you flip back over to what you did on the other page, didn't I find the function, its derivative, and plug the e squared back into it? It ends up being the same math that you did on this alternate definition. All right, check out what other ones did we do? Look at number 4. We did that at number 4.
Yeah.
So check it out. Oh man, more limit problems. What to do? I don't even recognize its definition. I plug a 4 in, I get 64 minus 64 over 4 minus 4 is 0 over 0. What can you do? Derivative of the top, 3, blah, squared times 2x minus 3. Doesn't that feel familiar? We did that before. What's the derivative of 64? Nothing. What's the derivative of x? 1. What's the derivative of negative 4? Nothing. So I'm left with this, and then what do? Plug the 4 back in, and yada, 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 240. It should feel like what I just did, but with a different approach. And honestly, it's a great resource because now, even on problems you did before with trig stuff, if you ever get 0 over 0 or infinity over infinity, you can just derivative the top, derivative the bottom, redo it. But make sure you show the limit again. Because if all I do is show this, APCalc is going to go, well, they got 1 point for the answer, but they didn't show they did new L'Hopital's rule, because L'Hopital's rule says redo the limit. So you need to state what you're doing right there. What other ones did we do?
7.
7? Okay, check out 7. Now here's the difference in number 7 and some of these others. On number 7, I've got 2 variables in there. Or do I? I think we have 1 variable, which is the h, because h is what's approaching 0. So what does that make x? A constant. I just don't know what constant it is yet. I don't know what to plug in for x in the end, like on the other problems we were doing. So I have to treat x like a constant. So what does that make cosine squared x?
0.
When you take the derivative of it, it makes it 0. That's why L'Hopital's is a little trickier on these. So literally, sometimes it's even helpful to go, you know what, I'm gonna put a 2 in there, or something like that, to really maybe, just for mental sake, I wouldn't write it in there, but sometimes thinking about it like it's a number might help you when it comes to taking the derivative. So here we go. I plug a 0 in, I get 0 over 0. So what do? Derivative of the top, which is 2 cosine 1 blah, times what? The derivative of the cosine, which is negative sine blah, which takes care of the cosine. And then what's the derivative of x plus h? 0 plus 1. Are y'all seeing that? Because the derivative of that is like a constant. That goes away, and the derivative of h is 1. So I really don't even need to write anything. So many people write 1 plus 1. And then they're dead in the water. So you got to recognize, if the variable is h, any other letter is considered a constant term. And that's why it's a little trickier with the x plus h stuff. And then on the bottom, oh, then by the way, what's the derivative of the cosine squared?
0.
It's tempting to write 2 cosine x times negative sine x, isn't it? Because you're used to that, but the derivative that's the variable. So x means it's a constant, and that would be a 0 then. Derivative on the bottom, and redo your limit. Now when I plug a 0 back in there for h, what do I get? 2 cosine x, right? Times negative sine of x minus 0. So that would be my derivative. Or if you really wanted to clean it up, negative 2 cosine x sine x.
Do we have to do that?
No.
Will you explain how you got 0, like minus 0?
Yes. Remember, anything that's not that variable is a constant. So that means x is I don't know what it is yet, but it is a constant in this problem. So it's kind of like having a 3 or a 30 degrees or something like that. And if I had 30 degrees there, you would have what? 3/4? We don't do degrees. I shouldn't do degrees. Say I had pi over 6 there. Right? And you know pi over 6, the sine of that is, the cosine of that is square root of 2. Yes. Square root of 3 over 2, and then if you square it, you get 3/4. So what's the derivative of 3/4? 0.
Okay.
You constantly have to think, if there's a variable that's not that in the limit, you treat it like it's a constant. And it's hard to get past that. And that's why if it's an x plus h definition like this, to me it's easier to go, wait, the function is cosine squared, the derivative is 2 cosine x times negative sine x, and I'm done. That's why I want you to know both. Because if it's an x plus h problem and the x and the h are still in there, to me it's easier just to grab the function, take the derivative of it. There's nothing to plug in for x. I'm out. But if there was a value like pi over 6 in there, I don't think it would have bothered you because you would have had this. Pi over 6 there, pi over 6 there. You would have recognized, oh yeah, the derivative of that's a 0, right? And you would have gotten down to here, and then you would have plugged the 0 in, and you would have had cosine of pi over 6 there. Once you plug the 0 in, and the sine of pi over 6, and you would have cleaned it up. But knowing both plans gives you a plan. And you get settled in and comfortable with one, and I think you'll be okay. Like right here, the 4 was already in there for x, wasn't it? So for this, L'Hopital's rule works great. It's not going to be confusing for me because it doesn't have two variables. So if I see this and I get 0 over 0, what do? What's the derivative of that? It's a fraction, so maybe you could raise it all to -1, or you could do the quotient rule. So how about this? Low times the derivative of 1. What's the derivative of 1? 0, so that's gone. Minus high times the derivative of low. What's the derivative of 4 plus h? 0 plus 1, so 1 over the low squared. Did y'all just see what I did? Low d high was gone. Minus high d low is 1 times 1 over the low squared. What's the derivative of 1/4? What's the derivative of h? Redo your limit. And you'll see, because the x is already in there, it doesn't bother me, right? Because the 4 is already in there, plug a 0 in there, and I get -1 over 4 squared, -1 over 16. Problem is, when the x is in there, and it looks like that, and people come down here and they go, wait, this part's not a problem, and a lot of times they go, wait a minute, isn't high d low, isn't the derivative of that 1 plus 1? Because they forget what's a variable, the h, what's the x? A constant. And they end up, because of that, they don't recognize that's a constant, they forget to take the derivative of that and get 0, or the derivative of that when they get there and get a 0. That's what makes it trickier. So what would I do in this case? If it were me, and I was a little do what? Use the definition and say, well, that's my function, and the derivative of that function ends up being this, and then I could just go back and plug the 4 in, if I had to. Right? Anyway, it's your call. Or if there was no 4 there at all, if it was just x, then I just stop right there. But it's your call. You got to get comfortable with what works for you. Practice makes better. It'd be great if practice made perfect, but I think all of us know that that's not always the case. But you got a better shot of pursuing perfection with practice. If you're not, I was just talking to a set of parents last period, and we're just saying, like, this person was like turning everything in on test day, or trying to turn it on test day and get it done the night before. It's just not the way. I know. Listen, I was a kid. I did the same thing at times. I'm telling you, if you get the habits of keeping up, you'll get to college. You won't even be studying on test days. If you prepare every night, like I used to do this, just cram the night before. I can't tell you how many times I saw the sunrise at the Alabama Pancake House out on Opelika Highway, drinking hot tea and coffee all night, stay awake. The sun comes up. I should walk into class. I turn it in. I'm like, man, I aced that thing. I get it back. And I'm like, what? And I look at my answers and go, what was I writing? And it looked so beautiful when I wrote it, but it was just bizarre. And then when I got into grad school, or actually my senior year, I changed my approach to stuff, and I just started studying like there was a test, even when there wasn't a test. I never studied. And I went all my nights free. I don't think I ever once studied for a test for 2 years, because I just stayed with it. And I remembered that stuff. I mean, whereas I didn't remember physics and thermodynamics and circuits and all that junk I took because I winged it and crash coursed it. And you might squeak a B out, but you don't. It's not going to be in the long-term memory. What you thinking? Not too bad? Okay, now I want to show you L'Hopital's rule on a couple other things. Check this out. Limit to infinity. So right here, if I were to plug an infinity in, I get e to the infinity. I know you can't really plug an infinity in, so that's what, but we're going to think about it. And in infinity here, I get an infinity squared. But isn't it pretty clear that a 2.7-ish to the infinity or an infinity squared is still infinity over infinity? So I have an infinity over an infinity. And this is another indeterminate form that allows me to use L'Hopital's rule. Now, if I do L'Hopital's rule with e to the x, what do I get? E to the x times the derivative of x, which is 1. So that actually doesn't change. What about if I take the derivative of this? 2x. And I redo my limit. Now what do I get? Still infinity. And this is what? 2 times infinity? Also infinity. But what's the difference between a 2 times infinity, right, and an infinity squared? An x squared is doing what? It's getting up to infinity a little quicker than a 2x is, isn't it? So with the top part, the power didn't change. But I still have infinity over infinity, which means I can still do what? L'Hopital's. So I take the derivative of the top again. I take the derivative of the bottom. Oh, now what happens? Now when I plug an infinity in, I get an infinity over 2. Well, now it's no longer a situation that I can use L'Hopital's with, but I can make sense of it. If I have a non-growing element on the bottom and a growing element on the top, what's that fraction approaching? Infinity. Now I need you to learn something from this because AP has a way of screwing with you unpleasantly like this. X to the 200th. Now I know if you were to graph this, and you're welcome to, the e to the x function is exponential. Does that. X to the 200th? Looks like that, at least to the right of 0. So if I'm approaching infinity, it looks like that x to the 200th is whoop, growing way faster, doesn't it? So the temptation is to go, oh, x to the 200 is going faster than e to the x. So this must, if the bottom's growing faster than the top, what should this fraction be? And the logic was great except for my premise, where I began. What I said was, the bottom's growing faster than the top. The thing that's bad about that is I was looking in the short term. In the short term it is. If I zoom out on this, you know what you're going to eventually see? As you move out, that x to the 200, which looks like it's shooting up, eventually over, that exponential starts going faster and growing faster and faster, and eventually the exponential function ends up on top. It would take a lot of manipulating on my calculator with this 200, but with like a, well heck, even an x squared, let's show you. I'll do it just with an x squared and I think you'll see it. Let's see if our calculator. Come on. Maybe it's coming. Can you analyze row? Hold up. Working slowly. Okay. All right, so check this out. I'm going to try to set up a window that will help you. Okay, so here is the first quadrant, and here is y equals x squared, and here is y equals e to the x. Okay, so that's not a good example. Okay, clearly the e to the x is bigger on all fronts, okay? But what if I change that x squared to an tenth. Ah, so right here, it looks like the x to the 10th is growing faster, doesn't it?
Yep.
And you're like, oh, if x to the 10th is growing faster and it was on the bottom, then this must be approaching 0. Okay, because it's growing faster on the bottom. But look what happens if I really change my window, and I have no idea what I'm going to have to change it to, but way bigger than that. That's to 100. Still, you're like, no way it's going to catch up. Like, I'm going to really jump on this one. A 1,000. What? Hold on.
Yeah, it's easy one to.
That reminds me, if I do this, I'm gonna have to go wider too. How about? Okay, I'm looking for the red getting on top. It is not invalid. This makes no sense to me why it's saying invalid. Min, max, min, max. Wow, I'm gonna really have to get up there. All right, let's get big time. I got plenty there, so let me just go to 50. How about, all right, what's that, 10? Come on, man. I am not lying. Somebody tell me right now, how do you know I'm not lying? No. Tell me. Because of L'Hopital's rule. Thank you. Okay?
How do we know that L'Hopital's rule is right? Because you told us that.
Because an old guy said it.
Because he stole it from Euler, man. And Euler's never wrong. Wow, I had no idea this would take this long. Okay, I'm just going to go big and go home. Here we go. I'm going to go to the 10th. Oh, I'm starting to see it though. It looks like it's closing the gap. I cannot believe how
Go to
high this is.
27, 30, 40.
Okay, here we go.
You gotta make that number big.
We're going really big. 20 and 18. I don't think this calculator's ever had to think this big. Come on, man.
It won't do it.
Really?
Maybe you need to increase your yeah, it wasn't
He doesn't check his
saying-
maps in 10 minutes.
Okay, I don't know why it's quitting on me. Loser.
Yeah, don't miss her.
Add an extra zero.
Maybe I can do it a different way.
Could you do it
Okay.
on like a computer program?
I guess the one thing I could try right now, since my calculator is completely sabotaging my example, is maybe just try this and just show you with a smaller power.
Oh yeah.
True.
You can see it.
You see that x to the 5th right here? Eventually it surpasses it. Okay? And like Sarah Parker said, I know that if this was x to the 20th, I know that if I keep doing L'Hopital's, right, I'm going to have 20x to the 19th. And then when I multiply the 19th, I'll something x to the 18th. And eventually I'm going to get down to a constant. And even though it will be a really big constant, if something constant on the bottom is beneath a rapidly growing number, the fraction is going to infinity, right? Bottom line is this. What's the fastest growing function we know in this class? Exponentials. So I don't give a crap on these. How big? Okay? It does not matter how big this number is in the bottom. Okay? If exponential is in there, it's always going to grow faster than a power function. And if you logically think through it, L'Hopital's plays that out. look at this one. What's gonna grow faster here? This is a natural log. Natural logs kind of look like this. This is a 1/3 or a cube root graph. It looks kind of like this. They kind of look like they're growing at the same rate. Kind of, but what could you do? Because when I plug in infinity, the log graph is going to infinity. The x to the 1/3 is going to infinity. But what do you have as an option? You've got L'Hopital's rule to think through that. Okay? So think through these problems, see what you can do on them. I hope I wasn't supposed to do any of that because I did get a little carried away. You've got derivative rules practice, a homework sheet on there. Yeah, there's a classwork on there where if you're missing the homework problems, maybe go back and work some more on the classwork problems. But guys, you really do need to get engaged on what you don't and don't know at this point. Are you with me? And let me help you. Come back and see me after school in the morning. Send me an email, and we'll see what we can do. All right. Good times.